So the title is called Optimal Experimental Design via a new regression minimization framework. This is a joint work in equal contribution order with grad student Yuanzhi Li from Princeton University, Artie Singh from CMU, and one of his students, Yiming Wang, also from CMU. Okay, so this talk is actually based on two things. One is our ICML paper with almost the same title, published this year. But after the paper has got published, we have improved the results. Like we get better bounds, we get a better algorithm, and this is what I'm going to talk about today. So for those of you who have been to my talk this March, talking about the matrix online optimization, this talk may ring a bell, but the algorithm in the end will be different. Okay, good. So the problem I want to focus on today is the following. So given data vectors, so in p-dimensional space, we have n vectors, x1 until xn, then we want to minimize the following function. That is, we want to select a subset of of cardinality at most k. We want to select a subset of them, and then we compute the covariance matrix with respect to the subset of the vectors we have picked, and then we want to minimize a function f on this matrix. So this is a function from PSD matrices to real values. So before I give you concrete assumptions on the function I'm going to assume today, let me first give you a little bit motivation about why I care about this problem. So everyone knows linear regression. That is, suppose we're given a data matrix of, say, n different data vectors, each in dimension p. So in particular, each line of the data matrix, we can view it as like a feature vector. For instance, for patients, say maybe the blood pressure, maybe the heart rate, and so on. And also, like, we may have observations. For instance, whether or not the patient has, like, say, cancer or not, or maybe the level of how strong the cancer is, how severe the cancer is. And whenever you have, like, a data matrix and observations, we can do linear regression. That is, we can do regression and find a vector y that's like a weight vector of the features. So this we all know is called like linear regression. So something I'm going to emphasize today is a problem called experiment design. So this is something that statisticians care really a lot, and also practitioners, motivated by the following scenario. Maybe in practice, it could be just expensive, maybe in terms of time or money, to observe each coordinate of BI. Okay, for instance, maybe we can have the full data matrix like almost for free, say getting the blood pressure of the patient could be cheap, but maybe to decide whether or not the patient has like a cancer that requires, I don't know, a number of like doctors sitting together in a room and maybe chat for like half a day or something. And therefore, a question that statisticians really care about is, what if we only have, say, a budget K? And now I need to decide which are the K patients, or more generally, which are the K rows we want to observe their corresponding BIs. Okay? And once you have, the corresponding BIs for those K rows, you can do a regression for those submatrix, and only with respect to the observed entries of B. So this is something that turns out to be very important. But so far, I haven't defined what I mean by the best K, right? So how could I decide if the first K rows is a better choice than the last K rows, for instance? So this comes into the issue of this comes into the notion of the so-called optimality criteria. So even like amongst the statisticians, they do not have a full agreement about what is the best, and therefore they come up with really a number of different optimality criteria. Oh, thank you for the speaker. They come up really with a number of optimality criteria that each of them has its meaning. Let me see how to use this. Okay. For instance, the so-called optimality criteria says that after you have picked, say, k different rows from the matrix, then you define that covariance matrix to be your sigma. Okay. Now you compute the matrix, the covariance matrix inverse, you compute the trace, and then divide it by the dimension. Okay. The reason they care about A optimality is as follows. That is, if you assume that there is an underlying like true weight vector, say y star, And if you additionally assume that each di is nothing but some x inner product with y, then plus some random Gaussian noise, like IID noise, then one can like mathematically formalize the question that is, if this is the model, and if you select like k sub rows, you can use linear regression to recover a vector y. Then how close is y to y star? Right? You can write that as a problem, and it turns out in order to minimize that Euclidean distance between y and y star, this is equivalent to minimize a function like this. So this is something like statisticians have very carefully studied, and it's called A optimality. People also care about other optimality criteria for like all sorts of different reasons that I am not even super clear why. Some of my co-authors are really experts. So if you are interested in the motivation, they will probably tell you more. So something else that is the D optimality, that's to like minimize the determinant of the covariance, like to then raise to some power, say -1/p. So those like, for instance, the raising to this power, like -1/p is just to normalize the problem so that if you scale the covariance matrix, this quantity like scales down by that same scalar factor. So it's just a normalization. And other optimalities people care about include like T optimality, like E optimality, V optimality, and G optimality. So these are the 6 most famous ones based on my knowledge to the problem. So let me now actually start to impose assumptions on the function f that I want to talk about today. That is, the first assumption I want to make on this function f is that it's monotone, meaning that if you have a matrix B that spatially dominates A, then I want the objective to be less than or equal to f of A. In other words, like if I care about the minimization problem above, then the more data vectors I choose, then I should have a smaller objective value. So I want monotonicity. By the way, spectral dominance, probably everyone knows, but to make sure, that is, we say A is spectrally dominated by B if B minus A is a matrix. That's PSD, positive semi-definite, meaning all of the eigenvalues are non-negative. So it turns out that one can verify all of these optimality criteria like satisfy this monotonicity. So therefore, we are happy to assume this as our first assumption. The second assumption we want to make is like f is reciprocal sublinear, meaning that if you put a scalar between 0 and 1 into the matrix, then this function is no larger than 1/t times fa. So at least for all of the 6 optimality criteria we study here, we actually have an equality, because if you scale it by constant, you can verify the normalization parameters are exactly to ensure that this happens. It turns out that the algorithm I'm going to tell you in the end only requires one side of this linearity, and therefore we are happy to make an assumption about what we call like reciprocal sublinearity of the function. So that's the second assumption I want to make. The last assumption I want to make in this talk on this function f is that it's convex. Okay? So it turns out, at least for 5 out of the 6 optimality constraints, in particular A, T, E, V, G, except D optimality, this function, one can verify that it's convex over the set of PSD matrices. But for D, it's actually okay because it's something called surrogate convex, meaning that there exists another function that behaves similar to the determinant whose like monotonicity is preserved, so that in order to minimize the original function f, which may not be convex in this case, the optimality is not convex, but there exists a function g, so that if you minimize g, that's equivalent to minimizing f. So that function g turns out to be the minus of the log determinant of the matrix, and that is because log determinant is concave, so the minus log determinant is convex, and therefore there exists a surrogate convex function G for D optimality. So for simplicity in this talk, you can feel free to ignore this subtlety like for D optimality, but just think about the original function f to be convex. Okay, so these are the 3 assumptions I want to make on the function f. Any questions before I move? Great. Now a few comments about essentially prior work. The first comment is that optimizing for D optimality is trivial because minimizing this function, then we see that the trace of the covariance matrix is sitting on the denominator, and therefore it suffices for us to maximize the trace of the covariance. Now, if using linearity of the trace, the trace of A plus B equals to the trace of A plus the trace of B, and therefore, if we only have a budget to choose like k different vectors, then we can just choose the k of them that have the largest trace. In other words, we just choose the k of them that have the largest like L2 norm square for the vector xi. Okay, and therefore T optimality, well understood. It's a trivial problem to solve. But it turns out that it's not really clear before our work about how to optimize for the other 5 optimalities. So the closest related work to this talk is actually done by Artis Singh and 2 of her students. So Yiming Wang, also one author of this paper, and another student, Yu. So they show that for A and V optimality, in particular, they can get 1 plus epsilon approximation to the original combinatorial problem. Remember, like the original problem asked us to find a subset of exact of size at most k, so it's really a combinatorial optimization problem. So they found a 1 plus epsilon approximation for that, assuming that k, which is the number of rows we pick, is at least like dimension square over epsilon. So this is what we have achieved, and to the best of our knowledge, the only 1 plus epsilon, and actually even the only constant approximation result before our work. So that's what they achieved. So this lower bound on k may not be very nice, because if the dimension, like the number of parameters, is like 100, then you need at least like 10,000 patients. So it may not be super super good, like in practice. They also have a second result. By improving the quadratic dependency for the dimension into almost linear, this might remind some of you about like vector graph theory, the number of vertices divided by epsilon square. It's, as we will see, like it's exactly that quantity. But they lose something. So first of all, they output a multiset instead of a set, meaning that in their final output, they may choose like the same vector multiple times. So this may not be realistic in practice, because it depends on the assumption. For instance, if you test the same patient twice, maybe you're going to get the same result, and therefore, like adding the same patient twice may not be useful, and therefore, like this result may not be applicable in practice because of this multi-set output. And also, their output their solution has an issue that we summarize as oversampling, meaning the following: the original problem asked us to optimize over, set of cardinality k, but they are going to output a solution with cardinality, say 2k, a constant times k. Therefore, it's not really an exact approximation algorithm, it's pseudo approximation. Like you output something whose cardinality is too large. But nevertheless, this is a good starting point for actually our project. So in their paper, they first look at the way they achieved that result, actually both results, is to first look at the continuous relaxation of the combinatorial problem. All right? Meaning that instead of choosing a set of cardinality k, you choose basically a real vector. Each coordinate is between 0 and 1, and then you have the total L1 norm to be at most k. So this problem turns out to be easily solvable because I have assumed like f is convex. Okay? You can just use convex optimization. Like in theory, you can use the ellipsoid method to conclude that it's polynomial time solvable. In practice, one can use mirror descent. That turns out to be a very practical algorithm. But then after this continuous relaxation, then all it boils down to is to do rounding. That is, we want to round this fractional solution with total L1 sum to be k, to round it to an integral vector, so that each coordinate is, like, say, between 0 and 1, and the total cardinality is at most k. So therefore, like, all we're left to do is to get rounding. So this is actually what I'm going to focus on for the rest of the talk. All right? So let's first see, like, what they do in the prior work. So they show that if you do a randomized rounding, that is, you pick the coordinates that proportional, in some sense, proportional to the weights that you obtain from the continuous solution, then you can get this 1 plus epsilon approximate solution, but with like 3 caveats. The first thing is, as I mentioned, that if you do this randomized rounding, somehow, like unavoidably, you have to redo the sampling process, like until you're really done, and therefore, like in the very end, all you can obtain is multi-set, meaning that you may choose the same vector xi multiple times. So at least according to my co-author, Yini Wang, like he said, this is intrinsic in their rounding algorithm, so there doesn't seem to be an easy way to avoid that. And the second caveat is that they recall oversampling, so they output a set whose cardinality is a constant times k as opposed to k. And the third caveat is, as I mentioned, that they recall the lower bound on the number of rows to be log dimension over epsilon square. And as we will see, this additional log factor is not needed. Okay, so we can actually get p over epsilon square. So let me actually say a few quick words about the oversampling. So oversampling gives rise to a solution that is not really an approximate solution to the original problem because the cardinality has changed, right? But one can actually turn that also into a true approximation by the following, into a true approximation like this. But unfortunately, you're going to lose a constant factor here in the approximation arrow. The reason is because you can actually replace the original problem. You can replace k over there by k over a constant. If you replace it that way, then it spells out a solution that's going to be, of cardinality at least at most k. So this can be taken care of. But if you rescale the problem with like k over c, you have to lose a factor of c like in the objective value, and that's why like oversampling is really bad, because if you make it into a real approximate solution, you're going to get only constant approximation, but not 1 plus epsilon. So this is the issue with oversampling. So in this talk, I'm going to show you a way to do rounding algorithmically that can achieve the same guarantee, but with exactly a set, without oversampling, and with k to be dimension over epsilon as well. So we're going to simultaneously fix all the 3 issues. In order to show this result, let me now claim that it suffices to solve the following simpler problem without even thinking about function f. Okay? That is, now I want to do the fractional rounding from this fractional solution pi to an integral vector s, so that the integral covariance matrix spectrally dominates 1 minus epsilon times the fractional covariance matrix. I claim that as long as we can guarantee this, then we automatically have the above inequality for any function f satisfying essentially the first 2 properties that we assume, convexity and monotonicity and the sublinearity. Here is the reason. If we have this spectral dominance, remember this one doesn't depend on the function, but you put the function on top of it, by monotonicity we have the first inequality. Okay? Now, by the reciprocal sublinearity, we can move the 1 minus epsilon out, and therefore we get this for any function f satisfying monotonicity and the reciprocal sublinearity. In particular, all of the optimality criteria people study in statistics. And therefore, for the remainder of the talk, I'm only going to tell you about how to do rounding so that this is satisfied without worrying about the function f. Okay? Good. So let me summarize the problem. That is, we now have a number of data vectors, n vectors, each in p-dimensional space. We have a fractional solution. And we want to find an integral solution with cardinality at most, I'm calling it the sparsity in the talk, like sparsity at most k, so that the covariance matrix, the integral covariance matrix, dominates 1 minus epsilon times the fractional covariance matrix. Okay, so this is now the problem I want to solve in the remainder of the talk. Good. So I claim that we can do another step of reduction to simplify the notations. That is, I can assume without loss of generality that my fractional covariance matrix is the identity matrix. Okay, here is the reason why. I can just do a change of variables. I can compute the fractional covariance matrix here. Then I do a change of variable. I just replace each xi with like b to the -1/2 times xi. If you do this change of variable, I claim that the problem below is the same as the problem above, except that now the fractional covariance matrix just becomes identity. So that's a simple change of variable. For those of you who care about the practical running time, I claim that you don't even ever need to compute b to the -1/2, because the algorithm you're going to see next will only depend on the inner products between vectors. And therefore, if you have a b to the -1/2 on one vector, you have another vector, whenever they're together, you'll only need to do matrix inversion. So, but that's a side remark. But therefore, for the rest of the talk, it suffices for us to solve this problem. Okay? Assuming that the fractional covariance matrix is identity. The overview of the rest of the talk is that I'm going to introduce a regret minimization framework for online matrix optimization to solve this problem. So this is a framework we proposed with Zhenyu Liao and Lorenzo Arricchia. We proposed actually 2 years ago that I also briefly talked about during my visit in March. But unfortunately, that framework itself is not sufficient to get the best possible result. So in this work, we added the swapping extension, a new algorithmic technique on top of that, which can eventually help us to solve this problem. So this is the overall plan of the rest of the talk. So from the next slide, I'm going to change the gear a little bit to talk about regret minimization. Is this plan good? Okay. Now, regret minimization. So consider the following online game. Let's forget about experiment design for a sec, okay? That is, we have a player and an oracle, okay? So the player in each iteration chooses a strategy, AT, from the following space, from the space of p-dimensional density matrices, meaning that p by p matrices that are PSD, positive semi-definite, and also the trace equals to 1. So for those of you who care about quantum, this means like a quantum density matrix. It's like a quantum mixed state, okay? So that's the action the player chooses in each iteration. Then the oracle spells out a feedback matrix that is, say, symmetric, and also p by p dimensional, okay? Now the so-called loss of the player at iteration t is the inner product between the loss matrix and his action or his or her action, which is denoted by the so-called kit things, and it's defined just to be the trace of the two matrices multiplied together. So this is the inner product between two matrices, and the so-called total loss of the player is just the total loss over all the iterations. And now the so-called regret of the player is nothing but the following difference. It's the difference between this total loss of the player he or she has suffered in the entire game, subtracted by, after seeing all of the loss matrices, what is the best strategy the player he or she could have played, in hindsight. So you compute this, and you compute the difference between these two. So this is known as the regret. And now the goal of regret minimization is to design a strategy for the player so that he or she can minimize regret. All right? So a very famous strategy that we're going to adopt today is the so-called follow the regularized strategy of the player. That is, in each iteration, say k+1, the player tries to minimize the following objective, a regularizer of the strategy, then plus a learning rate eta, a positive learning rate, times the loss he or she could have paid if for the previous rounds if he or she plays matrix Y. Okay, if we don't have the regularizer, this is the so-called follow the leader strategy of the player. So he or she just plays like the bad strategy against all the previous iterations. We know that could be bad, and it turns out that if one adds a regularizer, this can be like a better strategy for the player. And therefore, if you choose whenever you choose a different regularizer, that gives you a different strategy. All right. This is the follow the regularized leader update. Now, one of the most famous regularizers actually used for matrix optimization is the so-called matrix entropy function. That is the matrix times the log of the matrix minus identity. So if one uses the matrix entropy, I think it's actually the negative entropy, but whatever, then the player strategy has the following like simple closed form. That is, the player compute the sum of the loss matrices for all the previous iterations, then multiply that with some learning rate eta, then raise it to exponential e to the matrix, and then normalize it by some constant ck plus 1. That is the unique constant to make sure that after normalization you get a matrix with trace equals to 1. So this is the so-called matrix multiplicative weight update strategy that I bet a lot of you already are aware of. But in this talk, I'm going to use a somewhat better strategy that we introduced in this stock paper 2 years ago. That is, we propose to actually choose a different regularizor that is -2 times the trace of the square root of the matrix, which I'm going to motivate a bit later. But if you choose that strategy, that regularizer, it gives you a different strategy that looks like this. You sum up the loss matrices that you have seen in the past times some learning rate, and then you shift it by a constant times identity. And again, this constant is the unique constant to make sure that the summation thing is a PSD matrix, and then you compute that raised to the -2nd power. It becomes a matrix with trace equals to 1. So this is the explicit form of a strategy if you choose the regularizer to be the negative trace of the square root of the matrix. Okay? So in fact, in our paper, in that paper 2 years ago, we showed a general framework for any regularizer that is like the trace of a to the 1 minus 1 over q. But for this talk, it suffices to think about q equals to 2. That's good enough. And also, like, I haven't defined what better means here. So this better, this adjective better, doesn't mean like better always. It means that for certain applications, the strategy is better. So far, we have found like 3 applications. We know that it can give rise to faster algorithm for graph sparsification using this new strategy. We know that it can give rise to faster algorithm for online eigenvectors. And also the third application we found is this paper. I'm not sure if there's a 4th application yet, but we're on the way to find out. Good. So now let me use some pictures to illustrate a little bit the connections between these 2 strategies. So maybe the first one is very intuitive, right? You sum up the loss matrices. Then if you have some very large loss in some direction, then you want to penalize that and not play that too much. So the first one may be very intuitive, but I claim that the second one is just as intuitive as the first one for the following reason. If the loss matrices we have seen so far, if you sum them up, maybe say it's diagonal, for simplicity, if it looks like say 3, 2, 1. Now the matrix multiplicative weight strategy is going to give you like say e to the -3 eta, 2 eta, and negative eta, then normalized. But in fact, the strategy below is going to give you something that looks like this. So without even going into the math, one can actually quantitatively conclude that we have small, medium, large, meaning that at least in terms of the quantity of the values, like we still match large things to large things and medium things to medium things. So therefore, it should still make some sense. Okay. But what is more interesting here is actually a comparison between the 2 regularizers. So this is the entropy. Above is the picture for the entropy function, and below is the picture for this like square root of the matrix function in say only 3-dimensional space. So it turns out that the 2 regularizers look similar. Both, by the way, only like are defined over the space of the probability vectors, right? And therefore, like it's like a triangle-ish, like in a 3-dimensional space. Both like look similar, but as you can see, like the square root regularizer, like the derivative of the square root regularizer is like a bit more sharp when it gets closer to the boundary. So this is also related to things like say the log barrier function, the self-concordant barrier functions of like a set, which I don't want to go into, but it's somehow like having a sharper like gradient turns out to help the algorithm a bit better in terms of something. Okay, so that's like a picture to illustrate this strategy. So now, as I said, like in this paper we have picked this like new strategy from the paper 2 years ago, and we called it an L1/2 strategy because it's the 1/2 norm of the matrix. Then also like in our previous work, we showed a regret bound for this strategy as follows. That is, in each iteration, suppose the feedback vector is only, the feedback matrix is rank 1. It's like UU transpose in each iteration. Then we show the following regret bound holds. That is, for any strategy that you could play in hindsight, the regret defines to be what the player has like suffered for all the iterations minus the value of the strategy U for all the iterations. This regret is less or equal to the summation of the following two terms. So you don't need to read into the math at this point. But let me just quickly point out that the red terms are something that we typically refer to as the width term, and the red term is like a diameter term. So the blue terms here, the width term, are just like our monthly payment for our mortgage. So it's something like in each iteration, you pay an additional term here, and you sum it up over all the iterations. But the red term is like our down payment for the mortgage. You only pay it just once, and then you average it out. So that's at least the form of the regret bound. This is the regret bound we showed. Let's not even worry about the blue term because I'm going to simplify it. That is, one can actually move the f dot a part, the f inner product by a part to the right. That would just simplify this notion, this inequality. So these two inequalities are exactly equivalent. Okay. And now I claim that this regret inequality, the second one here, we can use it as a tool to help us to lower bound the minimal eigenvalue of a matrix. Okay? That is, I claim this inequality. If we now pick U, remember we haven't picked U, right? If we now pick U to be the rank 1 matrix corresponding to the minimal eigenvalue of the sum of the FT, okay? By the way, FTs are just the UU transpose. Then the left-hand side becomes exactly the minus lambda mean, the smallest eigenvalue of this matrix. And therefore, like if you revert the sign, you get this lower bound, which is a consequence of the regret inequality, but it helps you to actually it helps you to give a lower bound to the minimal eigenvalue of a matrix like this. Okay? So this is just one application of the regret inequality, and now I'm going to use this application, this like consequence, to show you how to do experiment design. Okay? So this is the same regret inequality from the previous slide I put in above. And remember that we have this problem from experiment design. That is, we have a fractional solution, pi, and now we want to find an integral rounding so that the integral covariance matrix especially dominates 1 minus epsilon times the fractional covariance matrix, but that's identity. In other words, we want to lower bound the minimal eigenvalue of this matrix, and we're going to use the inequality above to lower bound the eigenvalue. Okay? So that's what I'm going to do on this slide. So remember that I have already defined the player. So the player is going to follow the strategy from the follow the regularized leader, and therefore now the only flexibility for me as an algorithmic algorithm designer is to choose the adversary, choose what the oracle is going to do. So I'm going to define the oracle. Remember, the oracle chooses like ft equals to UU transpose. I'm going to define that oracle as follows. In each iteration, I want to define ut just to be one of the data vectors xi which maximizes this term, which maximizes like the minus of the down payment, every iteration. So it's like exactly this quantity above. I want to now pick the xi which maximizes this quantity. Okay? And how large could this quantity be? So let's use an averaging lemma to derive that. And I'm going to eventually show this. So on the numerator side, if I do a weighted average of the numerator, but weighted by pi I, remember pi is the fractional solution that I have now. If I do a weighted average for the numerator, by linearity, you can put the pi I inside. And remember the fractional covariance matrix is I. And remember AT is a strategy. So far, I haven't used any property about AT except the regret inequality. But AT is a mixed strategy, is like a density matrix, and therefore the trace equals to 1. Therefore, like the numerator, if you do the weighted average, is just 1. Okay? Over all data points. And for the denominator, if I also do a weighted average over all different xi's, then I claim that the denominator has 1 plus, eta times something, right? The one part sum up to k because the L1 norm of pi is k, right? And the second part, you can do the same thing. It becomes like eta times then the fractional covariance matrix, which is identity. And this becomes the trace of the square root of the matrix. But this, by Cauchy-Schwarz, you can get an upper bound to that. That is square root of the dimension. And therefore, like, we can get, using weighted average, we can get an upper bound to the denominator. But now by just averaging, we know that there exists some vector I, so that this term, this quantity, should be at least like 1 over this k plus eta times root p. And now I claim that we're almost just done for the following reason. So if we apply the regret bound, that's the regret bound, then in each iteration, we can get this gain, like, inside the summation. And therefore, if we do t iterations, we get this lower bound. Okay? Now, remember, I still haven't picked the learning rate eta. If I pick it to be, say, square root p over epsilon, then it simplifies to this. And now, remember, like, k, which is the number of rows I am allowed to choose, suppose that is lower bounded by dimension over epsilon square. That's an assumption I'm happy to make. Then you get this, and finally, if you do this algorithm for exactly k rounds, you can get 1 minus 2 epsilon. In other words, at this point, I have shown you how to get a set, how to get some output satisfying this, actually 1 minus 2 epsilon. But maybe some of you have noticed that as I'm going to output actually a multiset, but not a set, because in this averaging lemma, I am averaging actually over the entire set of vectors x1 through xn, but not through the set of the remaining vectors, and therefore I can only get a multiset here. So this is not yet perfect. But anyways, let me just mention that this is already an improvement over the previous result because, except the first issue, we have already fixed the second and the third issues. So let's now see like how to fix the issue about the multiset. Intuitively, we want to do averaging only over the set of remaining vectors. Let's see if that's going to work. So we can do the same thing, do a weighted average over the denominators. So the upper bound still works because it's only a subset of the things. But unfortunately for the numerator, if you do the calculation, you're going to miss a bit. So so originally we have exactly 1, but now it's 1 minus something. If you do the math very carefully, it turns out that this is lower bounded and almost exactly equal to 1 minus the lambda mean of the vectors you have already chosen. In other words, in the very beginning, you have chosen nothing, and therefore this lower bound is 1. That is good. But the kind of halfway through the algorithm, remember in the end we want the lambda mean to be 1 minus epsilon, right? So halfway through the algorithm, we get, say, a lower bound 1/2. Now you only make 1/2 of the progress you used to make. Then once you're like 3/4, good, like in terms of the eigenvalue, then you can only make 1/4 kind of progress. So kind of the amount of like reward becomes like diminishing as the algorithm goes. In the end, what we can show using this algorithm, using an averaging lemma like this, is to get, yes, a set, but unfortunately, we lose the sparsity. So we get an oversampling algorithm because you have to run this algorithm really for a constant times k number of iterations in order to get 1 minus epsilon. In other words, we can get rid of the multiset issue, but the oversampling goes back. So this was actually the result we submitted in that got accepted into XML. So that's not very nice, and therefore we continue to see like how we can resolve this issue. You kill one bug and another bug shows up. So that's what happened. So in the end, we discovered that there is actually the following variant of the regression equality that one can prove. That is, the regression equality above was actually like for each iteration you choose just the rank 1 matrix, okay, and then you lower bound the lambda mean. Then in this new paper, we showed that in each iteration, actually we can add a rank 2 matrix, meaning that we add some UU transpose and subtract by some VV transpose. That is, we can do a swap in each iteration. And then you get some regret bound. So let's see like why is this relevant to experiment design. In particular, we can actually start with an arbitrary matrix, say Z, that has something like rank K, meaning that we just pick, say the first K patients and define that to be a matrix. And now we start to do swaps. That is, in each iteration, we try to find the best possible vector we can add to the pool, and then we find the worst possible vector from the pool that we want to remove. So there are two things, two technical things that are needed in this process. First, one needs to get a good regret lemma about like adding something and removing something. So this we obtained in this paper. So it looks almost identical to the one above. So that's nice. It has two terms, like a red term, a blue term, and a red term. So basically, one term is helping you because adding someone is going to help you to get a better matrix, but subtracting a vector is going to help you, is going to hurt you, and therefore like you have a plus term and minus term, and that's the first technical thing that we showed in the paper. And the second thing is that that's the plan, right? We want to pick one to add and pick one so that the blue term is maximized. We want to pick one so that the red term, one from the set that of the vectors we have already picked, so that the red term is minimized. Then once you do the swap, you can invoke the theorem above. But one also needs to do a very delicate like averaging lemma to show that in fact there always exists a good blue term and always exists a bad red term, unless you're already done, unless like your matrix is already having the minimum eigenvalue that is large. Otherwise, this can always happen. And then we also show that this cannot happen too many times. In like roughly k over epsilon rounds, we can eventually just achieve like 1 minus epsilon for this for the minimum eigenvalue of the matrix under this minimum assumption. And now we output only a set without oversampling. So this is the new regret inequality we derived, followed with like a delicate averaging lemma, which I'm not going to show you today. So they're in the paper. In sum, we can now achieve 1 plus epsilon approximation in polynomial time for all of the optimality criteria above. And as I mentioned like briefly like a few slides ago, actually in parallel to this work, Mohit Singh and with Wei Junxie, they showed in this upcoming paper to Soda, which is I don't think this is online yet. But when Mohit was visiting us like 2 months ago, we communicated, and they told us that what they achieved is this lower bound on the number of rows for D optimality only. That is, you get only dimension over epsilon plus 1 over epsilon square. So it's very interesting, but we chatted and we don't think this technique generalized to other optimality. And also, we think some spectrograph theory lower bounds would imply that at least for the D optimality, one should not be able to get better than P over epsilon square. So, right, so there's a very interesting dichotomy here. That is, if you want generality for different optimality, you have to maybe lose something. But if you have specific algorithms for certain optimality, you can maybe do better. So that's actually what we have obtained and what they have obtained. So we're going to, both papers are not yet online, but we're going to put them online soon, maybe together. I don't know. So for those of you who care about a little bit about the experiments, so we compiled actually the naive uniform sampling thing as a baseline. That is, you just uniformly sample, all of the vectors, as well as like weighted sampling. This is essentially the prior work. But I think we decided to do the weighted sampling only over the set of vectors that are not yet chosen. So a very reasonable heuristic. And there's something that statisticians care about. That's an algorithm they call like Federoff's exchange algorithm, meaning that you start with a set of cardinality exactly k. Then in each iteration, you try to add something and subtract something so that the objective gets improved the best. So it's kind of similar to our idea, except that they directly look at the original objective. We looked at a regret minimization framework, which is different from theirs. So that's the so-called Federal exchange algorithm, and there's also the greedy removal algorithm by Avram and Boutsidis. So this algorithm does the following. You start with everything. Then in each iteration, you try to remove one vector from the pool so that your objective is decrease the minimal. Sorry, decrease the most, yes, whichever that makes sense. And so they actually prove something. They prove that for A optimality, this algorithm gives an n over k multiplicative arrow to the objective. So it's not necessarily a constant approximation, but it runs extremely well in practice. So I feel like there may be some missing theory behind this algorithm of greedy removal. And finally, it's our swapping algorithm. So we compiled 5 different algorithms for like 5 different optimality criteria, except for t, because for t, things are trivial. So there are 2 sets of numbers. The numbers outside the bracket are the objective values. The numbers inside the brackets are the running time. So the rough conclusion we can get is that also in practice, swapping and greedy are like 2 algorithms that outperform the others. And at the same time, swapping is an algorithm that's much faster than greedy for the following reason. Like the greedy algorithm starts with really the entire pool of vectors. Then you have to go through so each iteration you have to pick the one that decreases the objective more. But you have to do this like n iterations. So that means the complexity will be n². But our algorithm has a complexity that's only proportional to k times n. So if you pick k guys, each iteration you just do a linear scan over the best guy to pick, the worst guy to remove, but that's it. So the running time of our algorithm turns out to be better. So that's some like very preliminary simulations we did for the algorithm. And that's actually everything up to date. Thanks.